Hello and welcome back. In this video, we will discuss a bit more about the kind of inventory system under lean operations and analytics. And why is it lean? Why is it an inventory system? And what are its characteristics? Okay, so the whole idea is surrounding this notion called Kanban. Obviously, it is a Japanese term, and Japanese terms don't have a plural s behind, so this is like a romanized version plus a bit of English grammar. So multiple kanban becomes kanbans, right? So kanbans, uh, the kanji for Japanese term. So kanbans, right? What are these? It's like an inventory management system in terms of managing inventory. So if you recall, the inventory system has to give two recommendations, two guidelines, two numbers. One is when do we order, and second is how many do we order when we actually order, right? So in that sense, Kanban system being an inventory management system needs to provide those two guidelines, right? And how much, how many, when. First, let's take a look at how Kanban operates. You have a customer, right, and a producer. When we talk about inventory system, typically the physical distance between them will be a lot of kilometers. Uh, and furthermore, the producer is one company, the customer is one crowd, right, of independent people, consumers, or the downstream business that actually legally belongs to another company. So that's typically the idea when we talked about EOQ model, continuous review, periodic review. But since Kanban was originally an idea uh, from Toyota production, which is like all the systems done within Toyota, one company. So the customer, the notion of customer typically is more like the downstream resource workstation. So the downstream will consume the flow units produced by the upstream resource workstation, and thereby creating a supplier customer relationship. Right. So our supplier customer typically is the fruit store distributor selling fruits to our fruit store. That's the supplier customer relationship. But here we are talking about a closer physical distance, and also in terms of relationship belonging almost like to the same company, and in fact even more intimate than that, belonging to the same production line. So it's like on the same production line, uh, I am the supplier of value added flow units for downstream customer workstation to value add some more. Yeah, so from the lean perspective, each resource looks at the downstream workstation or resource as a customer rather than just another kind of me to operate on the flow units. Yeah. Okay. So that again, the view is slightly different, but that also changes the way we do various things, including the management of inventory. So the Kanbans will be uh, the empty containers, one at the customer site or workstation or the resource unit. The other one is at the producer's unit. So the idea is if we start with, let's say, both Kanbans all filled up, customer will begin to consume the flow units from his own Kanban, right? So it will take, let's say we are doing bread buns. So we'll take the bread buns and do baking or packaging, right? So we do baking, so bake and bake and bake. When this is empty, right, then the customer can then, uh, well, description wise, we say the customer brings this empty container down, but of course it can be mechanized, it can be automated using mechanics or robotics. So the customer brings this Kanban down to a already filled up Kanban, yeah, and swaps. And so the Kanban that is now filled with uh, ready buns for baking will be now taken back to the customer site, and the empty Kanban will be now at the producer site. Okay, two things happens now, right? Customer can then continue with the production, yeah, because the baking will continue and it is now having a full Kanban, right, with all the breads inside, ready for baking. Whereas the empty Kanban that is swapped with the producer's original full of bread Kanban is then a signal for the producer to start production. So as of course that implies that previously when the Kanban was filled up, producer would have halted or paused the production so that you don't keep producing and then falling to the floor and wasting, right? Because the whole idea of Kanban is to be lean, is to reduce waste. So this Kanban unit at the producer site is like a start-stop signal, right? It's a start-stop signal. When it's full, producer stops because demand is not fast enough. I've already filled up the bin. If demand is rapid enough, it would have been emptied out sooner. So I stop production. When the swap happens, the empty bin occurs, producer starts production. So therefore, producer itself needs to have some changes. Producer itself cannot be operating on timer cycle. Okay, produce 5 minutes, stop. Produce 5 minutes, stop. You cannot operate on that basis because you do that, you are blind to the frequency of swap, right? Because if I swap very quickly, it will be faster than your 5 minutes. You're not producing fast enough. If I'm swapping very slowly, like every 10 minutes, then I swap. But you are producing 2 batches, therefore wasting one whole batch of breads. So it cannot be a timer based. So logically, the producer has to have a production mechanism that is respecting this signal, isn't it? Yeah, it should have a start-stop system inside, respecting the empty bin and full bin signal. This kind of system imposes certain requirements, smartness, if you may, put onto the producer's mechanism, whether it is human producer or systems, robotics producer, right? So if it's human, you need to be a bit on the alert, a bit smart to look at the Kanban, right? Whether it's empty or full, and then produce or not produce accordingly. And if it's a robotics mechanical system, then you need to have a sensor to sense it. So it requires that smartness in the system, in the production system. Customer, same thing, right? So you need to have the ability to pause a little bit and incur a little bit of setup time. Now remember setup time? Setup time is when you process this batch, this Kanban batch of flow units. When it's empty, you need a setup time to refill. That is non-zero time. No matter whether you physically move it, customer moves it, producer supplies it, or have a robot that does the swapping, doesn't matter. You have to pause, right, for the proper detachment, swapping, then reattachment of the new Kanban. So no matter what, both sides will need some sort of smarter handling system, not just periodically ignoring all else and then just on a timer basis produce, consume. You're beginning to see that this already is very different description from the continuous review or periodic review system, where we never talked about this, right? We never had to talk about, please observe this signal. When it's full, don't produce. We never talk about that. So that's why it is not just an inventory system, but it is also a signaling system, communicating the needs, the downstream's needs to the upstream, right? And then of course, transporting the upstream's flow units downstream. At any point in time, you see that if the demand is very low, the swapping frequency will be very low as well, right? Because it takes a long time to consume the flow units in the Kanban. And therefore, the producer will not keep on producing only to see more and more finished inventory on the producer side, increasing holding costs, increasing the area of storage, yeah, and so on and so forth. Never. And when demand is very high, then the flow units inside consumers Kanban gets rapidly depleted. The swapping will be at a higher frequency, higher rate. And whenever this is empty, producer will start producing at a higher rate. And at this point in time, you can imagine that this Kanban cannot be done just locally between two systems. It will, right, logically have to be implemented further upstream and further upstream, and in the end, it just means all the way up or down the production line. The entire production line will be based on Kanban, so that when producer needs to produce more, it will empty out its own raw material Kanban and swap with further upstream, and be able to, with the penalty of a little bit of setup time, be able to be constantly filled with its own raw material input flow units. And that propagates further upstream, further upstream, further upstream, up until the initial purchase of raw material. So if you're talking about, say, buying flour, right, buying bags and bags of flour, then it will propagate further upstream to the purchasing department, the human purchasing department, who will then not initiate purchase if that department's Kanban's raw material, the flour, the bags of flour, is still full. It's still very, very high in inventory level. And when the Kanban swaps, right, that's a signal that the purchasing department should buy one whole batch of flour to get ready for the next signal. Yeah, so it will then propagate all the way. So when demand is low, they will hardly buy any for a long, long time. When demand is high, the signal gets propagated all the way upstream, and the purchasing department will buy, yes, up till the Kanban size, right? So it's like almost like a fixed order quantity, but at a much more rapid rate in order to cope with the higher demand. So in some sense, the Kanban system has the flavor of a continuous review system. There seems to be also a reorder point, right? Because when the Kanban on the customer side is empty, but total inventory in the production, there are two of them, right? So in that sense, there is still inventory in the producer's output Kanban. And so that is the reorder point. Whenever the customer's Kanban is emptied out, that's the reorder point. That's the signal to reorder as far as customer is concerned, right? So they swap and customer can continue instantly, whereas producer starts producing, whereas producer starts filling up. So there is some sense of a reorder point. And whenever customer purchase, they always purchase the fixed quantity, the size of the Kanban bin itself, the container itself. So if it can fit 10 dough, then that's the order size, right? If it fits 50 dough, then that's the order size. So fixed order quantity, reorder point. That's behaving like a continuous review system. Yeah. But the way Kanban works, devising the mechanism in this sense, signaling the production and stopping the production in that sense, is more than just a dumb push style inventory system. It passes the signal backwards. Therefore, in short, we summarize it as saying it's a pull system. Pulled by, that means the production is pulled by the demand. Demand is a wild animal. It can be suddenly high, suddenly low. We don't know. So pull system responds favorably and readily to the changes in demand. And favorably and readily means that it will not overproduce. It tends not to overproduce. It tends not to underproduce. So it will not overproduce because the most that it overproduces will be the Kanban. So if you keep that to an optimal level, reasonably sized, right? So as, for example, not to create too many swapping. Because if it's too small, then customer always will have to be starved, run out of flow units to process, and they have to swap and swap, and the setup time incurred will be very costly in terms of time. If it's too huge, then of course it defeats the purpose. You're going to produce a lot and it becomes a big inventory holding cost, right? So with a reasonably sized bin size, the Kanban size, uh, and the number of bins. So you can also have 2 bins on the customer side, 2 bins on the producer's output side, right? So as to um, be visible, very visible on the quantum of signaling. So it's this Kanban. Oh, we're down to the last Kanban. So activate, something like that. So it's very quantized, right? So in continuous review, we just talk about the flow units, almost like a continuum of flow units, tires, inventories. But in Kanban, there's some sort of a batch idea or quantized idea, right? Like this batch, this collection of flow units in the Kanban bin. The next Kanban bin has this number of flow units. Okay, so there are variations in there, and basically there's some throttling. You don't overproduce, you don't underproduce. You kind of like the leanness you can have, right? We don't want to be overweight, we don't want to be underweight, so we have some level of fat. You cannot have zero fat. That will be disastrous to your health, right? But you can have some level of fat, the optimal level of fat, and that is the whole idea here as well. So with the signaling being the difference, right, that will basically make it a lot more attractive because all the resources will have to obey or respect that Kanban's signal and become a little bit more cooperative, a little bit more respectful of the demand and changes, right? And of course, a little bit smarter in reacting to the fluctuations. Okay, so that's the basic idea. And of course, being an inventory system, it has to answer 2 questions. When do you order? And when you do order, uh, how much do you order? Yeah. So let's look at the when to order. So in terms of when to order, it will be that when the user empties the container, right? Then the card is put on the receiving post, whether it's a card or some sort of a email electronically or some sort of a lighting if the stations are near enough to physically see each other's light being lighted up. All these are just signaling mechanism. So when it says the card is put on the receiving post, empty container is taken to the storage area, and so on, it's just to pass that message, so to speak, right? The signal that customers needs some more, right? And producer, please prepare your work. So this acts as a signal to produce. So when to order, whenever the customer's input Kanban is emptied out. That's one way to talk about. Of course, we can vary that definition. It can be that, you know, if there are 2 input Kanbans to customer, when, so long as the first Kanban bin is emptied out, we start to reorder, we start to swap so that there's no setup time. The customer immediately works on the second Kanban, like very little to zero setup time, and then someone, maybe a manual worker or a robot or whatnot, can take its own time, 5 minutes, 10 minutes, right? Take out the first empty Kanban bin, move it to the producer's output bin, swap and bring back, producer's already filled up Kanban back here, right? Something like that, right? So you can make all kinds of variations to adapt or to improve further based on your local needs. But the idea is you need to swap. Yeah. So that's to swap the Kanban. Whereas if you recall, earlier in the continuous review, periodic review, we never talk about all these things. We just say, oh, supplier delivers everything and 5,000 tires, all 5,000 will go into your warehouse. I order 1,000 tires, all 1,000 will go into your warehouse. And we never talk about these, the bin and its function, its exclusive uh, size which acts like an order quantity, but the swapping, which acts like a signal for production. We never talk about that. That's kind of unique to Kanban, right? So it's also a signaling mechanism. When to order, right? How many to order? That's even easier. That's just the container size, right? The container size you define. Now, of course, we need to also be aware of what size is good. The cost, the holding cost that is incurred onto the company is, of course, the total um, flow units inside all the Kanbans. So it will be like two parameters, right? So if you're the operations manager here, you will have two parameters to work on. Yes, the total number of flow units is what we are concerned with, but it is the product of number of Kanban bins and the Kanban size. So you can have one big container of 50 units, or you can choose to have 10 smaller containers, right, of 5 units. Or you choose somewhere in between, 5 containers of 10 units. They are all incurring roughly the same amount of holding costs for the company. But one way is probably more agile than the other, right? Leaner than the other, based on the idea of safety stock, right? Service level. So how likely do you want the customer's demand to be denied out of stock? Out of stock means what? In a production line, when the customer, the resource, the machine, right, that needs to be filled with flow units, and you deprive it, right? You deprive it with the flow units. You don't supply to them, or you take a long, long time to supply to them. Then what happens? The resource has to stop starving. You're starving the resource. You're starving the customer machine or team from having work to do, and so they just idle, and that's a waste. That's a waste. So, uh, due to various things, right? The production's delay, long setup time, fluctuating setup time, and various things like that. So the safety stock will be providing a buffer, a cushion against more environmental uncertainties than just the demand fluctuation alone. So demand fluctuation, yes. Customer is a workstation, so it will have its own customer as well, and it has to face that fluctuation. And everybody, so is everybody. Earlier on, we just worry about that. That's all. But here you need to worry about additional things, right? The time it takes to swap, the setup time, right, and production delays, and various other things. So that's why you also have a safety stock here. And the way it goes is based on Little's law. Based on Little's law, right? So the overall inventory is the flow rate times the flow time plus some kind of safety stock. This safety stock is going to be the buffer to cushion against fluctuations against various things, not just demand, not only, but including demand fluctuations, but also other things. So fluctuations in setup time, lead time, and all that. And the way it goes is the formula looks a little bit complicated, but it's actually very simple. K times C is the number of containers times the size of each container. Will give you the size in terms of number of flow units per container. So K times C will give you the overall inventory, right? We're just talking about here, not the entire production line. So the total inventory um, in that particular section of analysis. And that has to be following Little's law. Remember Little's law? Little's law only works when there's steady state equilibrium. So we're talking about during production time, the flow rate times the flow time will give you the WIP. And we want to also add some, maybe 10%, 20%, depending on how risky, how succumbing to fluctuations is the situation at your production site. So flow time. Flow time is the time it takes, right, for the waiting time. So there is some sort of a buffer, this Kanban itself. If you are one of the flow units, say you're sunk at the bottom, you are at the customer station, but you are not yet being processed. That's almost like a queue system. Like this triangle is a queue, not in first come first serve basis, but it's anyone comes, anyone serve basis. But that's fine. So this is a queue, and this is the server. So if you recall the queuing theory, right? So this is the queue, this is the server. And if you are one of those that are stuck at the bottom here, you'll be processed last, right? And you have the longest waiting time, the T cube that we talked about. So that waiting time average with the first dough that is being pulled immediately, that's almost like zero waiting time. On average, right, that will give you the waiting time. Plus, every single flow units will go through the processing. Some a bit longer, some a bit shorter. So average processing time. And that would mean the time it takes for any particular flow unit to wait roughly on a W bar minutes basis or seconds basis, roughly on a P bar processing time basis, right, to come out from the processing system. So that would be the average daily demand times, that means the flow rate times the flow time through the customer workstation. This 1 plus A is basically reflecting the safety stock. 1 means 100% of this, and plus some additional percentage, because A is a number between 0 to 1. The Kanban theory says it's a policy variable. Now, this policy is more like how scared are you? The fear factor. If you are very scared, you feel that there's a lot of fluctuations, right? And you need more standby units so that your customer server doesn't choke, doesn't starve. Then you want to have standby, like 100% standby. That's the highest you can go, 100% standby. And if you are very certain, that your operations, your processing time, everything is very reliable, then you can set this lower. Of course, during tests and quizzes, it may be set to 0, right? But in real life, it's probably 5%, 10%. Right? So the higher it goes, the higher the holding cost. But you need that, right? If you feel that there is a lot of fluctuations, there's a good chance that my customer station might be starved of the necessary flow units. Then I better have a higher amount of standby, like 2 Kanban bins here, right? Double the size. Huh? Okay. So actually, this is very reasonable based on Little's law. And that's it, because that's answering the 2 important number questions about the inventory policy, and also the distinction between Kanban and the typical continuous review system. Let's look at the money side. How does Kanban help in terms of making the system leaner? Now, already we saw qualitatively how the mechanism, right, by signaling, we sense that, yeah, that's true, right? Producer just don't blindly just produce based on I can produce, so I produce a lot, right? And if you cannot absorb fast enough, I'll just hold it at my output area. No, not really. So we kind of set a limit to how much you can produce, and after that, producer, please stop. So you have to respect that signal, and then you must have a start-stop mechanism. We said that. But if you look at the 2 graphs over here, and particularly looking at this so-called traditional as continuous review, because that's more comparable, then you find that the cost curves, which is the U-shaped curves, all right, the U-shaped curves, the 2 cost curves are showing distinct differences, right? So this is traditional, this is on the right side is the Kanban. The traditional total cost per year, annual inventory management cost, that means not adding the purchase cost. Therefore, it is not affected by the cost of the unit itself, right? But just based on additional stuff, additional payments, expenses to store the goods, to procure the goods, to transport the goods, and so on, right? So all these are required costs. The traditional continuous review, all right, is the sum of the holding cost and the setup cost. And no matter whether the optimal quantity, right, like that attracts the lowest cost, no matter where it is at this point, right, the orange curve, orange line here. Yeah. And it is high compared to Kanban, because Kanban, the ordering quantity and also the optimal quantity, the bottom of the U shape occurs at a lower point on the y-axis. That's the most important one, because the y-axis is the cost, the total cost, and that's what we are talking about. So it will be lowered, all right, whether usually is significant, right? But even if it's marginal, why would you want to purposely operate at a higher cost knowingly, right? So as furthermore, it is significantly lower, all right, so lower optimal cost. So if you choose the right quantity, the order quantity, right, the Kanban size, then you will experience optimal total cost that is lower than the optimal total cost if you should just do the push style of continuous review inventory system that doesn't care much about the day-to-day demand fluctuations. It only plans for the whole year. Right. So that is the whole idea. You notice that in Kanban system, the when to order, all right, how many to order, they never quite talk about annual demand. They are a lot more localized in terms of timing. They're talking about the now or the next few moments. At most, it's probably the next day. So they're not talking about a macro time scale, but a more micro, more localized time scale. And therefore, if there is fluctuation in demand, presumably, right, the gradient will be a lot smaller, right? So your fluctuation cannot be from changing from 10 units to 100 units. It's likely to change from 10 units to 12 units, right? 15 units, that's already 50%. Yeah, but annual wise, you might have 1 year selling 5,000 tires, another year selling 6,000 tires. That's a lot, right? And another year, as business grows, you may be selling 7,000 tires. And in a bad year, maybe you're selling half, 2,500 tires. So that overall change is a lot bigger, a lot more massive than the local fluctuations. And Kanban deals with the micro fluctuations, right? So next stage customer, or next stage, my next stage resource in the same production line is my customer. So that's the micro in terms of the space and micro in terms of time. You see, at no part do we look at a year kind of demand. We look at daily average demand. That's it, right? So that's the primary differences. And of course, the lean part of it not only is in the logic, but also the total cost. So of course, we would want to do this. Hence, final conclusion, in lean perspective, pull is always better than push. Let me say that again. Pull system in inventory management is always better than push system. And one example, one methodology in implementing pull is none other than Kanban. Whereas for push, we talked about continuous review, a special case being the EOQ model, and also the periodic review. Okay, so that's the landscape. Next, let's look at quickly, because the calculations are very simple, but just want to kind of walk through very quickly some examples. So I'm talking about auto parts here. Container spends 0.02 day. I need to standardize the timing to the same units, then it makes sense. So spends 0.02 day in processing, 0.08 day in materials handling and waiting to be processed. Daily demand, so that's the flow unit. The flow rate. The stock, safety stock equivalent of 10% of inventory. That's the A policy variable. Okay, so if each container can contain up to 22 parts, how many containers should be deployed? So you just write down the uh, given parameters, the numbers, into the necessary variables, right? So the flow rate, processing time, waiting time, the policy variable, the container size, and say container size times the number of Kanbans, right? How many containers must equal to the right hand side. So the flow rate times flow time times 1 plus A, the policy variable. That's it, right? So solve for K, you get it. Suppose a proposal to revise the plant layout would cut materials handling and waiting time per container. That means cut the queue time, TQ time, to 0.06. Just now was 0.08. So now contrast. How many containers do we need? So from 10 down to 8. So all these are to see, how whether it is cost justifiable. Typically these containers are rather cheap plastic containers. I mean, unless you're talking about super high tech, I don't know, wafer production or whatnot, electrostatic, super clean, dust free. That's a different story. Then the containers might be very expensive. I don't know, but typically these containers are the, uh, you know, plastic containers. You can even buy a pair and call it a Kanban. That's cheap. Usually that's cheap. So you can say, well, I'm saving 2 containers. So typically that doesn't really uh, uh, make for an impressive slide on your presentation. But cutting down the handling and waiting, the queue time, right, from 0.08 day to 0.06 day. Any time cut is usually going to be, number one, expensive. Number two, also um, very impactful. That means very helpful to the production line. So the question then is, how much does it cost for that factory, that processing line, to reduce from 0.08 to 0.06? Now remember, this is waiting time, TQ. If you recall the TQ formula, one good way is to reduce the standard deviation. Then the CVA, CVP will be reduced, and then you can get some good results uh, with a relatively lower cost, right? Than to reduce the processing time and increase the number of servers and all that. So yeah, all these are very simple as far as test question is concerned. In this new setup, find the number of containers. Oh, it has reduced from 10 to 8. But I'm just trying to give you some real life context why we want to do all these. Okay. Next example, 2 examples actually. Item on the left side, the example 2. Item B52R, hope nothing to do with the B52 bomber, has an average daily demand, that's the flow rate, right? Average waiting time is 0.5 days, so waiting time W. Holds 100 units container size, right? The processing time is 0.1 day. The units day and day will have to be the same before you substitute it. If the policy variable is 10%, how many containers? So same calculation, right? So we plug in, we solve for K. The idea is here to round up. Clearly we cannot round down, because if the ideal container is 6.6, then what happens to the 0.6 times 100? That's 60 units. Where are they going to be stored, right? They're going to be hanging around on the floor. So we have to round up. Last example, again, the question, right, gives you all the parameters. It will be your job to read and extract out the numbers, daily demand. So that's our D, right, our daily demand. Waiting time plus processing time, 0.8 plus 0.2. Then the policy number, we don't know. They want us to find, so we find, because left side is defined, right side is one unknown, so we can solve for A, right? What is the total planned inventory? That's our WIP. So that's the left hand side, which is 270 times 20. That's it, right? Suppose the policy, and this is to test your understanding. So if you're very good with mathematics, but you don't know what the numbers mean, then too bad. So in this kind of course, whether it's business operations, lean operations, I've seen students who are very good with math, but they don't necessarily get A plus because their math is good, right? So you have to have the some ground sense and familiarity with the meaning of those terminologies, right? Just because the formulas look the same doesn't mean that the meanings associated with them are the same. Yeah, so we talked about that before. And what is the plan? Sorry. Suppose the policy variable now has been changed to 0. That in real life means that the operations is now very stable, very reliable. It gives a strong sense of confidence that there is no risk of fluctuations. And if there is, it's a very minor one. And we can definitely absorb the shock without uh, extra buffer flow units. How many containers will be needed now, right? So originally we needed 20. With very stable operations, we don't need the buffers. So the number of containers, 12. 12, right? Only 12. Only 12. So that means at each of the input Kanban area for the customer resource workstation, it will be reduced. And if the container doesn't cost much, it might be that the area, right, especially for expensive areas like Singapore, uh, the rental of the space is very premium. So if the area that's required to hold the containers is reduced, that's a good thing, right? That can help reduce the overall size of the factory and help to reduce the either the rental cost or the building cost and so on. All right. So that's all I have to say about Kanban. I'll see you in the next video session.